Welcome, focused learners, to another explainer. Today, we're tackling a topic that sounds kind of intimidating on paper, but actually, it's an absolute masterpiece of engineering elegance. We're looking at the underlying blueprint of Cascade Control architectures. Now, if you've ever struggled with getting an advanced dynamic response out of a system, and you literally dread the idea of needing a perfectly exact process model to pull it off, well, this explainer is going to be a revelation for you. Okay, let's dive into this. Here's our roadmap for today. First, the problem of dead time. Second, the dual loop architecture. Third, collapsing the inner loop. Fourth, we'll run through a case study on ore milling. And finally, we'll wrap up with the universal cascade principle.
All right, part one, the problem of dead time, specifically looking at thermal lag in a continuously stirred tank reactor.
Picture this physical setup in your mind. We've got a massive tank trying to maintain a very specific final product temperature. The primary controller is monitoring the bulk temperature and adjusting the coolant valve at the bottom. But here's the agonizing part. That controller is completely, blissfully blind to what's happening inside the cooling jacket itself. If the coolant suddenly gets warmer from the supply line, our primary controller has absolutely no idea, until that warmer coolant slowly, gradually alters the entire massive tank's bulk temperature. It's kind of like trying to drive a car by only looking in your rearview mirror, right? It's a blind controller fighting a battle where it's always inherently reacting too late.
Let's trace this fatal flaw sequence step by step. Step 1. A disturbance hits the coolant temperature. Step 2. We hit the dreaded dead time. The massive thermal bulk of the tank slowly, sluggishly heats up, while our controller just sits there, completely unaware. Step 3. The primary sensor finally detects the temperature error. And Step 4. The controller desperately reacts and opens the valve further. But honestly, it's already over. Off-spec ruined product has already exited the tank. By relying on a single, delayed sensor, this system is fundamentally doomed from the start.
Moving on to section 2, the dual loop architecture, or what I like to call the interceptor narrative.
We can fundamentally change the game just by adding a second sensor and controller. Now, what's really interesting about this setup is that instead of waiting for the bulk tank temperature to change, we now have a fast, secondary loop actively monitoring the coolant directly. When that coolant disturbance hits, this secondary loop detects it instantly. It corrects the valve position before the main process is ever severely impacted. We're literally intercepting the threat at the perimeter.
So, conceptualizing this as an abstract block diagram, we can really clearly see the genius of the architecture. I want you to visualize the outer primary loop as the big picture manager. It's looking at the ultimate goal, the final product temperature. But inside it, working away, is the secondary loop. Think of this as the frontline worker. It's embedded directly at the point of disturbance, ready to intercept issues before the manager even needs to know about them.
To put it simply, let's contrast these two roles. The primary loop is your master process. It's relatively slow, and its main job is to set the reference target for the worker. The secondary, or inner loop, is the slave process. It's incredibly fast, and its sole purpose is to intercept those disturbances. Cascade Control architecture isn't just taking two controllers and letting them fight for dominance. It's a beautifully structured, highly efficient delegation of responsibility.
Section 3. Collapsing the inner loop. This is where we get to the magic of the math.
When you run the mathematical derivation for the secondary loop, you uncover a really neat trick. By taking the open loop transfer function and converting it into a closed loop transfer function, we achieve something amazing. We can mathematically collapse that entire, complex inner loop, the controller, the process, the feedback, and treat the whole shebang as a single, highly robust, predictable block within the primary system. We've simplified our architecture by essentially black-boxing those fast dynamics.
When we plug that collapsed block back into the global system, something profound happens to our disturbances, and this brilliantly illustrates the true superpower of Cascade Control, the attenuation factor.
So why does this matter so much? Well, mathematically, the controller gain is in the denominator. That means if you tune a high inner loop gain, it actively shrinks the effect of the physical disturbance to near zero. I mean, before that coolant fluctuation ever has a chance to reach the main tank, the math forces its impact to vanish. The architecture itself totally nullifies the physical threat.
Section 4. Let's look at a case study, ore milling, and solving mechanical mass flow.
Imagine an industrial setting, a massive 2,000 kilowatt iron ore milling plant. The physical constraint here is tough. We've got vibratory feeders dropping raw ore onto a long conveyor belt that feeds the primary mill. The problem? Varying ore density unpredictably alters the actual mass hitting the belt. But without Cascade Control, The primary mill motor sensor has no idea the feed rate dropped until that empty patch of belt completely traverses the conveyor and physically causes a massive drop in the mill's power draw. This transport delay, this mechanical dead time, is absolutely unacceptable for grinding efficiency.
So how do we fix it? We eliminate the dead time by introducing a conveyor cascade. We just add a secondary sensor, a conveyor weight scale directly under the belt, right after the feeders. Now, when the ore density drops, this inner loop intercepts that mass flow disturbance instantly. It ramps up the feeder vibration frequency before that empty patch of belt ever makes it to the mill. The primary mill motor never experiences a drastic power drop, all because our secondary loop intercepted it perfectly.
Which brings us to Section 5, the Universal Cascade Principle, Synthesis and Rules.
What's absolutely beautiful about these controller design rules is that you rarely need highly advanced, complex model-based tuning. For the inner secondary loop, proportional or P-only control is often totally perfect. The goal there is just maximum speed. A steady-state offset, that's totally acceptable here, because any baseline drift will naturally be caught and managed by the outer loop anyway. That outer primary loop uses your standard PI or PID control for absolute setpoint tracking, where error has to be eliminated. The big takeaway for us is that standard PID families are perfectly sufficient, proving just how inherently robust and forgiving this Cascade architecture really is. Let's move to the summary and see how this builds the complete picture. On one hand, we have the CSTR, a thermodynamic chemical process where we manipulate fluid valves to intercept supply temperature fluctuations. On the other hand, we have ore milling, a heavy mechanical mass flow process where we manipulate feeder vibration to intercept ore density drops. You're looking at two radically different physical realities, completely distinct sets of variables, and yet they're both mastered by the exact same structural solution.
Which leads us to this final thought. The profound insight of Cascade Control. Diverse physical realities, whether exothermic heat transfer or heavy mass flow, are governed by a singular, elegant mathematical architecture. This isn't just a clever trick for tuning controllers, guys. It's a fundamental insight into how we map out and master dynamics in the physical world. Thanks for joining me for this explainer. So the next time you face a stubborn, sluggish system completely blinded by dead time, I want you to ask yourself, where can I build my inner loop? Where is my interceptor?